far we have seen how two layers can cooperate with each other, and then how the address resolution can be facilitated. So, now what we will try to see, we will talk about, we have already started talking about that there is a means as time progresses, there is a huge crunch of giving or distributing the IP addresses, because too many devices are coming up with the advent of IoT and Internet of Everything. Probably huge number of IP addresses are required. Already there is a solution, that IPv6 with 128 bit address, but that is a long term solution of course. But currently, as we have talked about, that network should be interoperable, network should be gradually moving towards that final destination or final modification. So, that is one thing, and second thing is it must coexist with the previous one being still there, and with that we should be able to resolve some of the issues. So, that is something which we will be talking about. Means meanwhile, what people have thought about resolving this issue of IP address crunch. So, what happens, it is actually first let us talk about this, how do I provide IP addresses to user. Suppose user is first time booting, at that point how can I give him the IP address, because if he is in the network he needs to have a unique ID, otherwise his identification is not unique. So, nobody can forward packet to him and he will jeopardize the operation of the networking. So, everybody who is connected to the network is connected to LAN, and then through LAN, through router, probably in the internet, he must have a unique ID, otherwise we have a big problem. Okay. So, if that is the case, one way is that whoever is booting that machine, so he actually first go hard code the IP address over there, he has to keep a repository which IP address I am distributing where. This is a very cumbersome process, it is a manual process, it might be erroneous, the person might misplace what he is putting where, he might forget, he might put accidentally duplicate address. So, that will create huge amount of problem. Whomever he wants to forward the packet, if there is a duplicacy, he will router will not understand, he will learn that okay, this particular IP address is connected to some other port, he will forward it accidentally to others. So, proper networking will not be happening. So, if that is the case, can we automate this process? Initially people started thinking about that. So, what is the process of automation? So, automation might be something like that, this IP address repository I can keep it somewhere. Okay. So, and we can actually distribute that. So, we can call that as a address repository or a server which keeps that. We will give the name later on after the concept is fully developed, but right now we can talk about that repository. So, somebody in the LAN, suppose inside a LAN somebody is keeping all these IP addresses, list of IP addresses that can be distributed among the machines. Whenever the machines are coming up, so they are first time booting, so immediately what can happen, they might, now it is the reverse thing which will be happening. Okay. So, basically what will happen, because the machine has its own network card, so it has its MAC ID, IP address might not be there. So, MAC ID he will have. So, now what he can do, just reverse of ARP. So, he might with that MAC ID he might say this is my MAC ID, he can broadcast, because he knows that central repository who has all the list of IP addresses that has to be allocated is already there in the LAN. If it is there in the LAN, then he can just broadcast it, okay, hoping that this guy will respond back. Okay. So, he will give the MAC ID and he will say I do not know my IP address. So, can anybody, he just broadcast this message, can anybody help me, what should be my IP address. So, once he broadcasts, that will also go over here, because it is a broadcast domain. So, the entire LAN, all the packets will be transmitted. He will see that, he will see which IP addresses are already being allocated and what are free. Among those free, one of them he will be taking. That is why it is called dynamic host configuration protocol. So, that is why this is also called DHCP server. So, DHCP server, that repository, he keeps all these addresses and also he keeps a flag whether this address has been allocated or not allocated. If allocated, he means puts an entry that this is already allocated, this cannot be further allocated, otherwise there will be duplication. If some of them are not allocated, he picks one of them randomly, that is why it is called dynamic host configuration. So, for the host he is configuring the IP address. So, that is why it is called dynamic host configuration protocol. So, he picks that ID and then he replies him back with his MAC ID. He has already supplied his MAC ID, he is telling that this is my MAC ID, I do not know my IP, and he tells okay, in the layer 2 he replies back with his MAC ID that this is your ID and that should be your IP address. So, immediately he takes that means layer 2 packet, he learns the IP address, he puts the IP address inside his particular OS and network card. Okay. So, immediately he will be knowing his IP address. So, this is how he discovers his own IP addresses. What is the advantage of this? We will talk about why we have been talking about this IP address crunch, how this helps, we will talk about that later. So, this might happen. Now, the problem is then every LAN must have a DHCP server. This might not be happening. Your entire institute might have a DHCP server or it might be somewhere else. Okay. Somewhere your internet service provider might have that DHCP server, okay, somewhere in the WAN, in some remote server. Now, every station they can only broadcast, they cannot broadcast packet to everywhere, because if everybody starts doing that, the entire network will be flooded by those broadcasting messages and the entire network will be choked. So, generally this broadcasting is not allowed beyond your LAN. Okay. So, you can only broadcast messages within the LAN. So, that is why every LAN will have at least one machine configured as this DHCP proxy. Okay. So, almost similar like our ARP proxy. So, DHCP proxy, what it will do? It will actually take that message and he knows the IP address of the DHCP server wherever it is. It might go beyond the router, beyond the even gateway to the internet, somewhere else, whatever it is, this DHCP server, it has a IP address, that IP address he knows. So, he knows the address of the DHCP server. So, he becomes a bridge between this guy's connectivity towards the DHCP server. So, he, because for this guy he does not even know IP address. So, he can only generate that layer 2 broadcasting telling that this is my MAC address, I do not know my IP address, somebody can help me. So, this proxy will take that, okay, or DHCP relay we can call it. This relay will take that, he will then put this MAC ID and tell okay, for corresponding to this MAC ID can you supply a particular IP address. He will forward that packet. Now, that packet is going from him only, he knows his IP address, his MAC address, he knows this IP address. So, immediately he can transmit this packet. So, that packet like earlier we have discussed. So, that packet will go through the entire network to DHCP server, DHCP server will give that IP address to him, then he actually replies him back telling that okay, this MAC ID now I have resolved, it should have this IP address, and he will give that IP address, and whatever IP address he takes, DHCP server already will be aware of that because he has only configured this IP address. So, he will tick that IP address which has been taken by this particular host. So, every time a host comes up, he will be taking this IP addresses from the DHCP server, and this will be continuing. If this happens, why this is advantageous? This is advantageous because it is like this. This DHCP server, what he can do? He can be like the network service provider. So, network service provider will reserve some of the IP addresses, but he will subscribe multiple more users compared to as many address he has. And what he will be hoping that not all the users simultaneously will be using his service. So, with that hope, and generally in networking that happens, in the peak hour also you will see only few users among all the users will be utilizing it. Okay. If that is the case, it is kind of statistical multiplexing of addresses. Okay. So, you have limited number of addresses, now you have so many users, but you know that all users will not be active simultaneously. So, what you do for the time being, you give him a temporary address. Okay. So, you give him an address, whatever time he is using it, you keep him with that address, and then whenever he releases it, then immediately you take that address as if it is available and give it to some other guy. Now, next time you come up and again try to connect, you might not be getting the same address, you might be getting another free address which is currently available with the DHCP server. So, this is what DHCP server does, and that is why it is also called dynamic host configuration protocol. And with this you might be also means helping yourself towards reducing the unnecessary blockage of IP addresses. So, basically you take a huge pool of IP addresses, whichever users are active you randomly allocate them all these addresses, and then whenever somebody is releasing it, you take that, you declare that as if that is free, next user ask for it, you randomly again allocate those addresses. So, this is how DHCP at least at the beginning helps IP to reduce this or to combat this address crunch of IPv4. So, basically you can serve a large number of pool of users without giving them all unique ID. You can actually take large number of, again smaller than that large number of users, some number of IP addresses which are unique, and then you randomly allocate them to all these guys. So, what will be happening while they are communicating, they have a certain IP address for the entire session, they will have that IP address. At that session they are means all the packets will be delivered correctly to them. Whenever the session expires, he actually means he goes away from the network, he is no longer utilizing it, then DHCP server will take that IP address, give it to somebody else, and whenever you require he will be giving some other things. At that session your IP address will be that only. So, the IP address of the host keep on changing over time, but it does not hamper his communication with the network. At the time of his communication he will have a unique IP address, because that is what DHCP server makes sure. So, this will be happening. So, that is how DHCP at least solves one part of IP address crunch. We will also see NAT, it is again a cross layer thing with the transport layer, that also resolves some of the issues of IP address crunch, it by locally using some locally unique ID, but not globally unique ID. So, that can be reused in multiple locality. That is something also we will see whenever you are doing local routing, that is possible, and also global routing is also possible with the help of TCP layer, the above layer. Okay. But before that we should be also starting to discuss how these routing table entries are being learned, how the routers in a distributed fashion knows about if I have to send this packet to somebody, which should be the next router, what should be my next hop, which port I should connect to. How this is being done, that is something which we will be discussing. This is a distributed protocol, generally router exchange messages, control messages among themselves. So, if I have a complicated network, let us say I have a graph G where multiple routers are connected among themselves in a complicated networking fashion or network connectivity. Okay. So, these are all router, let us say router 1, router 2, router 3, router 4, router 5, router 6. Okay. So, what I need to know is from a particular host will be connected, he has a IP address, another host who is connected, he has another IP address. So, from here to here if I go, what should be my strategy, which router I should choose from hop to hop. So, he must know where I should forward. So, if he is choosing this path, then he will be giving it to him, then he must know where I should forward next. Otherwise, they might take a longer route, unnecessarily the packet will be delayed, and unnecessarily all the routes will be congested, because all packets are going via longer route, it is staying in the network for longer duration, within that time more number of packets will be coming. So, the entire network will get more and more congested. So, what is this particular thing that routers does among themselves in a distributed fashion, and they resolve this, what should be the next hop, and then what should be the next to next hop, and so on. Every router decide what should be the next hop for a particular source destination pair of a packet. So, this is something we will be trying to understand. So, basically what this boils down to a problem which is well known as the shortest path finding. Okay. Shortest path computation or finding shortest path between two nodes. So, one router to another router, what is the shortest path? Now, shortest might be, it is an ambiguous definition. What is shortest? Is it distance wise shortest or is it delay wise shortest? So, it by means as you define different things, accordingly the shortest path definition also will be changing. So, if I talk about physical distance, then I have to find out what is the smallest physical distance, because in a very complicated network there are multiple paths to reach from R1 to let us say R6 I want to reach. It can be this one, it can be this one, it can be this one, it can be this one. So, there are multiple paths through which I can reach to a particular router. Now, distance wise probably this will be, if you by inspection, if you see, of course, I have to provide the distance of each of the link, we will see that this is the shortest distance. Therefore, if I decide that this is the shortest distance, so whenever there is a request from router 1 to router 6, always I should go via router 4. That means, router 1 should know that among router 2, router 4 and router 5, which are his immediate next neighbor, I must choose router 4, because I am trying to reach router 6. And router 4 also must know that among my neighbors like router 5, router 2 and router 6, he must choose router 6. So, this is the shortest path, because this is shortest distance. Sometimes it might be just delay, I might try to see what is the delay happening in the overall these things, and locally I might be able to decide that what should be the shortest path. Okay. Sometimes it is not the local shortest next hop. As you can see that I have to go from R1 to R6, the shortest path includes the longest next neighbor. So, remember, this is not as simple as we are thinking about. It should be seen end to end, and then only I can come up with the shortest path strategy. So, how in a very complicated mesh architecture with multiple routers, maybe thousands of routers or maybe even more, some millions of routers, with a very complicated network with lot of edges and this many nodes, how do I really construct from a particular node to another node what should be the shortest path. So, there are multiple, you probably are aware of, there are multiple such shortest path algorithms which are there. One of the famous one is Dijkstra. Okay. So, we will try to see that Dijkstra one, and then probably we will go to the original shortest path algorithm that has been implemented in internet protocol. So, we will also talk about those things. If time permits, link state protocol for routing we will talk about, then we will talk about this Belmont-Ford algorithm also. So, we will see how far we can do, but at least what we will try to do, we will try to see what is the algorithm instead of going into the, because all shortest path are, because it is shortest. So, it is a optimization problem. So, we will have to define a proper optimization problem, that how do I define a shortest path, and then how do I solve this optimization problem in a very big network with lot of nodes, lot of edges. That is a optimization problem. We will not go into the details of that optimization problem, how that can be optimally solved, what is the algorithm. So, we will just give the algorithm that has been proposed without proving anything about its why it is, means what kind of complexity it holds, why it is optimal, even though it is, we will see that it is greedy, locally greedy, but why it is optimal. So, all those things we will not do, but we will this course is not for that. There should be a separate course of network optimization, but in this course we will just try to give the essence of what is the algorithm. Okay. So, let us try to see, we will take an example and then try to demonstrate. So, let us see a particular network. So, let us say this is the network. So, it is node A, B, C, D, E, F, G and H. Okay. So, whenever you are trying to do a shortest path, of course, this link must give some weight value. It might be distance, it might be delay, whatever the metric is according to which you are trying to calculate the shortest path, but that value should be given, then only your shortest path algorithm will come into picture. So, this link weightage are very important. So, let us take the link weightage to 7, 2, 6, 1, 2, 4, 3, 2, 3, 2. Okay. Now, in this, from node A, starting from node A, we will try to calculate the shortest path to every other node. That is what Dijkstra came up with. So, we will try to see his algorithm. Okay. We will just see the algorithm, why it is optimal, what is the complexity of it, why it is efficient than others. We will not talk about that. We will just try to see how this algorithm functions actually, that part only we will be covering. So, what it does from the starting node, so it has steps. So, we will be describing those steps. So, from the starting node A, it will try to see what are the next neighbor that he can connect to. Okay. So, as you can see, A can connect to B and G. Now, you try to actually give the cost that it incur to go from A if you take that path. So, suppose from A you go to B, so the cost is 2. So, you put 2 over here, and from where it is coming, the immediate previous node. So, from A it is coming to B with cost 2. Over here it is cost 6, it is coming from A, you write that. Okay. Now, these are the only two you can connect to. So, now you actually make them, these are temporary nodes that you have visited now. So, only B and G you could visit. Okay. Among this temporary node, some of the nodes you will be making permanent. So, what is the technique? You try to see. So, basically what you will be doing, for every node initially this cost you will put as infinity. Okay. And because you have not explored them, so you do not know, so you put a dash that I do not know from which node it has to reach. So, every other node will have infinity and dash, infinity and dash, and so on. So, this will be there for every other node, only these two nodes are now populated. So, among these nodes, now you try to find out what is having the lowest number. That means, that node can be reached from A in the shortest amount of cost. So, that node you make permanent. So, every pass you actually make one node permanent, okay, whichever has the shortest cost. So, now I have A and B, two permanent nodes. Now, let us try to see from there which are the other node I can reach. So, from A I know already G I could reach. So, G will have the same value, but now from B I can reach to, as you can see, E and C. So, now I have to update their cost and corresponding this thing, update their cost and the corresponding previous node. So, B I can reach from B, and what is the cost of E? 2 plus 2. So, that is 4, and C I can reach, first number will be 4 and then second number will be B. So, the cost is 4 and it will be B, and over here the cost will be 2 plus 7. So, that should be 9 and it is B. Okay. Now, what are the next nodes that you have explored? G, E and B. Let us try to see among them what is the lowest, that now I will make permanent. So, now E is the lowest, so I will make E permanent. Done. Now, I will try to see from E whom I can reach. Okay. So, E, what are the new nodes I can reach? I can reach F and I can reach also G. If a earlier visited node which has been, means which has the cost updated, but if I now get, I will also check if I can now go from here the cost is 4 from A, if I start via this path the cost is 4, and from here if I go further and reach G I will be adding 1. So, 4, this will become 5. So, I will update this and I will change it, that no longer I have a shortest path to G via means A, but it is actually via this E. So, therefore, the previous node is E. Now, as you can see, slowly I am now constructing this path. So, you can see earlier I had A to G, that was the shortest path with 6 cost. Now, I have found another path, as you can see, trace it back E previous node, E to B, B to A, because B previous node is A. So, A, B, E, G, that is giving me cost 5. So, therefore, that is the one. From E any other node I can reach? As you can see, I can reach over here, from C also, because means sorry, I can reach F. So, let's update that cost of F. What is that? 4 plus 2, that is 6, and it is coming from E. Okay. Right now from F and B, okay, nothing else we can reach. So, this is where I will end, and I will try to see this cost is 5, this is 6, this is 9, these are infinity. So, therefore, now G will become permanent. So, now from G I will try to see whom I can reach. Okay. So, from G to H, and this is how it will continue after all the pass, means I reach my all the nodes, or all the nodes are permanent. You will see that the shortest paths are formed, and I will be able to trace them back, what is the shortest path for every node. Like over here G has become permanent. Now, you can see from A to G the shortest path is this one, A to E the shortest path is this one, and so on. A to B shortest path is this one. Okay. This is how from A to every other node I will be now getting the shortest path. If you continue this algorithm till the end, you will see that all the shortest path will be found. So, that is Dijkstra algorithm. It is a very simple algorithm, but it works in a scalable fashion. It converges always, because after means every time, every iteration you are making one node permanent. So, as many nodes are there, that many iteration you will be doing. So, it converges, guaranteed convergence, and also it is very fast. It is we can prove the complexity of the algorithm. We are not doing it over here, that is for other course, but it is a very low complexity algorithm. So, this is how generally for every node if you have the picture of the graph, you will be able to calculate the shortest path. Okay. So, this is something Dijkstra's algorithm, if you run, every node will be able to calculate his shortest path to every other node. So, for that the entire graph is to be known. So, how you can know this graph? Basically every node can broadcast what is his neighbor to other nodes. By seeing all these broadcast messages, and means if you aggregate, so every broadcast he will get the broadcast of the neighbors also, and neighbors will get the broadcast of his neighbor. So, like this, if you aggregate all these things, you will be able to construct the whole graph. Once you know the whole graph and associated links, then you can actually compute or run this shortest path algorithm, and you will be immediately able to think about what should be the next hop for a particular link I am trying to reach. So, everybody knows from him to whichever destination he is targeting, what should be the shortest path, which direction he has to go. So, A knows if I have to go to G, I have to forward to B. B also knows if I have to go to G, I have to forward to E. E knows if I have to go to G, I have to forward to this. So, they knows this immediately, and they will be able to implement that. So, this is one of the protocol. Next time what we will be trying to do, there is another protocol which will be more simpler probably. So, we will start talking about that Bellman-Ford algorithm. That is another way of determining the shortest path. We will talk about that, we will talk about pros and cons, and then link state protocol most probably will not have time for that, but that is another protocol that you should learn, because that is the protocol which is being used in IP mostly. So, we will talk about that later. Okay. Thank you.